Good morning to everyone. I think we need to start. We have some exciting speakers lined up, and I think we should make use of the time. I'm sure that there will be people coming and going, but let's get started with somehow the final tracks, the final sessions in the track 1, Global Sustainable Aviation. The ICAS Congress is also nearing its end, but two of the highlights, I may call that, of this track 1, Global Sustainable Aviation, are in front of us. So we have first the session with the OEMs, and I would also like to mention already the session just afterwards, which is the sessions about the operations view on technologies. So we are going to see a view on the air traffic management from a European, from a US perspective, a view on contrails. Is it worthwhile performing the trade-offs, flying around the contrails to the detriment of fuel burn and CO2, obviously? And finally, and I think that's also a very important element, to see what does the final customer, the airline, think about it. So we're going to have Lufthansa here in order to present us a view. But let's now start with the OEMs. So we have lined up the 4 OEMs, and I think we're just speaking about it, covering today 99-point-something% of the global delivery. Will be an interesting discussion maybe as well to see how that's going to look like in 20 years from now. I may ask them later on whether the 99-point-something% is going to be maintained, or whether the share of the 4 is going to be decreased over time. So what we are going to see here from Airbus, Boeing, Embraer and ATR is their overview, their individual overview about their sustainability strategy. And I think it's very important to look at what those OEMs are doing, because in the end they are integrating all those different technology bricks into their products, offering those final products to the airline community. And I think it's as always it's a balance between risk and reward. And in terms of risk, every new technology, every change is a risk, obviously. But there are rewards which are expected either by the airline community or also by society. And I think how to manage that, because when you think about the OEMs, they have to provide performance guarantees, operational reliability, maintenance cost, fuel burn, and that needs to be guaranteed. And if those guarantees are not being met, the penalties are awful. And I think this is the view we'd like to get out of that session today, to see between risk and reward, how to manage that and how to make sure that we are progressing fast enough. On the other hand, staying as low risk as even possible. So that's it. I would like to start then with the first speaker, and you see that here on the panel. We have Isabelle Bloy. Isabelle is head of products and services strategy at Airbus Commercial. She has a strong engineering background. She was the chief engineer of the A321XLR, and before she grew up in the aircraft architect environment, leading with her team the A380 autopilot, and she also participated and led some R&D projects. So strong technical background. I'm sure she can tell us a lot about what Airbus sustainability strategy with the technical repercussions is. Thank you, and Isabelle, it's all yours.
The same size, just June. So good morning, everyone. I'm very happy to be with you to talk about the sustainability journey of Airbus Commercial. There is one thing that you said. I have a strong engineering background now, being head of strategy. The thing that I can testify, and we had a few words already across the OEM, is that an aircraft is a very technical answer to a very non-technical question. And sustainability is part of this non-technical question, which has to do with our planet boundaries, with our social future. And I think that it is a unique opportunity to share our vision, our various vision, because it's basically the way we will ask the question to the entire ecosystem. And how we are doing that, and is there any difference or convergence in between ourselves. So first, I would like to come back to our purpose. The purpose of the AIRBUS group have evolved over time, and I would like to put the sustainability in a wider context. Sustainability means, of course, something which is related to our planet boundaries, our capability to sustain a trajectory over time, but it's also sustainability of our aviation business. Which means that today we are wording our purpose as we pioneer a sustainable aerospace for a safe and united world. And the words which is important, I think, for this conference is very much pioneer and sustainable. And pioneer, what does that mean? It means still exploring new technology, but also exploring various aircraft configuration and what it means on our business, on our customer. So this is something which has to do with our capability to discover, to go deep into the topics, but then to be capable to reintegrate that at aircraft level. However, the technical things is not the only thing, and it's what I was saying. Basically, what's important is, yes, we want to lead the aerospace, the clean aerospace journey, but there is the how we are doing it. Of course, we want to foster diversities. It's the way we are doing our business. It's also a bit the way Airbus has been built. Over time, we have a diverse, I would say, roots. But the third pillar that you see here is super important, meaning that we are built on a requirement of safety and quality. And when we are talking about new technologies and introduction of these new technology into the business, understanding what means these requirements in aviation on safety and quality is obviously of very high importance. Because it will be exactly the balance between the risk and the opportunity that Axel was just mentioning. So how we do it will be part of the discussion on the maturity of the technology that we have. So to have a journey towards, first, if we want to talk about sustainability, we need to agree on what is the end point. And one thing which is super important is that we have agreed, and Airbus is supporting, the 2050 target about the decarbonization journey of the aerospace for a net zero emission by 2050. Agreeing on that endpoint is already a big thing, is a kind of a polar star for our industry. But to make it concrete for our engineers, to make it concrete to our partners, we need to split that down into intermediate target. And this is what we are doing with the target to 2030 and the target to 2035. And then you will see how we are drawing a path. So in this journey that I want to share with you, I want to talk first about the steps which are required to get there. So first we are drawing a path. Second, we are filling it with ideas and we are integrated. Third, we are building ecosystem. And fourth, we are building our competencies. So here we are starting with drawing the path. 2030 in aviation, it's tomorrow. What are we targeting? We are targeting things about how we produce and how we make our fleet compatible with the solution that we have immediately, to have an impact quite quickly, I would say, on the various indicators that we could have. So I don't know, I suppose that you are super familiar with the scope 1, 2, and 3. Scope 1 and 2 in the reporting is everything how we produce, so is the carbon footprint of how we are producing our aircrafts. And scope 3 is the carbon footprint of our sold product, upstream and downstream. Just to give an idea, of course, the carbon footprint of the aviation is 99%. Based on the scope 3. 1% is the scope 1 and 2. And among these carbon footprint of the scope 3, you have 2% for the ground operation and the rest is flight operation. So let's put it in the context. I think it's important still that in the frame of what I was saying, what are the questions that we are asking to our business to answer, that even if you have this strong imbalance between the carbon impact of what's flying and the carbon impact of the rest of the operation, it shouldn't hide what we should do for the entire business. So 2030 is focused on reducing by 63% the scope 1 and 2 of the industrial emissions, and also to offer 100% SAF compatibility of our product. Why? Because you see that in our decarbonization journey, and it's true for all of us, the replacement of the fleet is super important. I will come back on it, but basically just 30% of what's flying is latest generation, which means that we have something to do in this industry, and we have already committed on a ramp-up for the industry. And so this means that we need also to show that having this ramp-up is not more impactful for the climate in general. So it's how we run our business. Then sustainable aviation fuel, as I will show later, is one of the energy vectors we are relying on for decarbonization. And so we need to work now on how to make it fully compatible with 100% SAF, even if today our current fleet is already 50% compatible. 2035 is a big milestone, and I will show in the next slide. The next slide you will have been shown by the other stakeholder from Airbus having joined this conference. But this is our journey towards 2050 with these mid-milestones, reducing by 46% the CO2 emission for commercial aircraft. This is an important milestone because it will be based on a number of pillars, but it also is putting a point to which we need to go then to 2050. And here it comes to the question from the ICAS, what are the technology that we have in the basket for our product entering in the next decade, capable to make the difference between 2035 and 2050. Also, in 2035, we want to be the first manufacturer to market a hydrogen-powered aircraft, and we had Glenn Llewellyn having a talk. It was, I think, on Monday, on the hydrogen-powered aircraft, because we think that it's part of our duty to explore alternate ways and alternate energy vector. So all this means that we need to have a menu, because in front of a community, which is by university, partners, supplier, other OEM, regulatory bodies, we need to split the work in such a way that we are asking the right question. And we have split the work into product intensity, operation, sustainable aviation fuel, and disruptive technology. Disruptive technology being mainly the hydrogen-powered aircraft, but also everything which is, I would say, breaking the usual pattern of our aircraft configuration. In this, of course, we have everything around the fleet replacement. So the latest generation of aircraft, we shall not hide that we have already done a lot because CO2 is a major metric for our competitiveness of our aircraft. If I give the example of the A321XLR, for instance, just certified in July and that will enter into service by the end of the year, we are 30% better versus the previous generation. It has nothing to do with the competition, it has only to do with the generation of aircraft. And this is true for a number of our aircraft at the latest generation that we need to renew. However, the big and the major challenge that we have now in front of us is what is the product of the future. So what is the product of the future? I have touched a word on the hydrogen, but what is the new single aisle, what is the new wide body, and what are the ingredients? The ingredients in an aircraft is always a bit the same. So you have propulsion, you have aerodynamics, and you have the system. You had a detailed discussion yesterday with Frank about investigating propulsion and especially new propulsion system. I think that here I want to manage expectation, because of course, as long as we don't have the answer and the demonstration on certain technology, it's very difficult to say how it will turn into a product. So we have that strategy to work with the ecosystem in order to understand what is the key parameters that goes along this technology, whether it makes really a difference. It's a bit the question revolutionary or evolutionary, and how this revolution, if ever there is, would change the configuration of the overall aircraft. So where you are integrating your engines, what are you expecting, what does that mean for the customer in terms of operation? And so we are doing this kind of convergence loop together with the R&T. So the R&T is developing the technology. Then we have a first answer that we can get either through demonstration, simulation, analysis. Then we are making, I would say, our loop at aircraft level. And then we are seeing whether we have cliff effects on the configuration of the aircraft, yes or no. And in the case we have, then we are restating another question to the business so that the entire community can work again. This is the case on the open fan. This is the case on the UHBR, for instance. And the integration of the open fan is by itself, I would say, a challenge at aircraft level. So not only we have this for the propulsion system, as has been already explained also during the individual conference, we have the same type of discussion for the wing and the same type of discussion for everything which is related to weight, like, for instance, fuselage and wing materials. Something which is a bit less in the focus of immediate, I would say, fuel burn targets is also everything which is related to smart automation. And we see that the various items that I present here on the screen, meaning technology for latest generation of aircraft, operation, sustainable aviation fuel, somehow they are also linked through the type of technology and research that we are doing. I'll give you an example. When I was talking about smart automation, this is very much an enablement for trajectory management. Trajectory management that we are looking for, both, I would say, in the non-CO2 discussion. So I understand that there will be a presentation on non-CO2. What is the trade-off between carbon and non-CO2 impact? But also having trajectory which are carbon efficient. So there is a full ecosystem having both digitalization purposes, smart automation around the product, connectivity, which is working on several pillars. So we see that we have pillars, which are our own cluster of questions at OEM level. Then in the community, there is investigation for technology, but one technology can serve different purposes. And that's the way I think we need to build our ecosystem around key questions. So smart automation is part of it. Also, between operation and sustainable aviation fuel on Airbus side, we have made last year an extensive campaign on single aisle around emission for sustainable aviation fuel. Because of course it's more an ecosystem discussion. So we have energy provider, infrastructure, etc. But we need to be capable to answer key questions about how it behaves, what does that mean for the aircraft, the impact on the components for the fuel tanks, for instance, the emission, and what it means. So we are doing, and we are using our platform to fly and to help the community to answer better what are the key questions we need to answer to go to 100% SAF and to have the right specification for this product. And I will go back on it when we are talking about ecosystem. So, same for the non-CO2. We had very recently a campaign on contrails. This is more linked to the disruptive technology in the frame of the hydrogen. We were flying to understand the contrails creation for hydrogen-powered aircraft and the back-to-back that we have. Because it's of true importance for all of us to understand the, I would say, the fundamental physics of the non-CO2 aspect of aviation, because otherwise we cannot have the right answer. So we are contributing to this in the frame of our normal, I would say, type of aircraft, and also in the frame of the disruptive technology. I will not talk so much about the market-based measures, even if we have projects around carbon capture, because it's not the core of what we are doing, and I think it's not the core of what you are doing in the ICAS ecosystem. One thing I would like to spend some time is, yes, we have said that there is several pillars, there is several ways of achieving it, but in Airbus we are also looking at the entire life cycle of the aircraft. And again, we understand that the flight life is most probably the most efficient way of achieving something for carbon, but we have other type of topics for sustainability, like material scarcity, like non-CO2, which are, I would say, sort of hidden behind the very high KPI, or key indicator, of the carbon metrics. So it means that it goes from design to end of life, recycling, and not often we are talking about how an OEM is working across its own life cycle, because it tells something about what we are doing in-house and what we are doing with our supply chain, with our partners, meaning institutes, for instance, and with other industrial partners like energy provider or recycling company. And we have a joint venture, probably you know, that is in charge of recycling. So we are working with our supply chain, and we are also working on manufacturing and manufacturability, because of course when you go for something which is a bit more innovative, you need to have the manufacturing which goes with it, and the manufacturing is linked also to the end-of-life recycling. Which means that all of this that I have described is a convergence between the OEM and the full ecosystem. And we had great achievements. The question that we need to have is how we are building our ecosystem, and what do we get out of it? And for instance, what we have done on the multifunctional fuselage demonstration in the frame of Clean Sky 2, that was a European project, it's demonstrating manufacturing capability. We are talking here more about material, we are talking about recyclability and manufacturing capability, which is at the heart of what we are doing. Yes, we want to have an innovative aircraft, but we want to have something that we can produce and that we can ramp up. So, ecosystem is absolutely key, all the more that sometimes we are not the major lever. And if you look at what we need to have for sustainable aviation fuel and H2, so hydrogen, of course, the enablers is not the OEM, but we need to ask the right question. So I think that on sustainability, we have one polar star, which is really something which is common to the aviation. And you know, I have the feeling that it's a bit like the board games. You know, my kids, they are fans of board games. And in the past, either you win, either you lose. And now you have a lot of collaborative games around one goal. And I think that sustainability for aviation is the one goal target. As a conclusion, I said we need to draw a path. Then we need to fill it with ID and integrate at aircraft level. We need to build an ecosystem which is consistent. At the end, we need to have people. Because we have built over the past century a know-how how to make vehicles heavier than air flying. This is a know-how not belonging to private companies. It is a know-how for mankind. We need to transmit that for the safety of aviation and for the long-term existence of aviation. And for this, we need to attract talents, which means that we need to have a sense of purpose. So this type of framework and collaboration is an opportunity to grow new competency for aviation and also to attract new type of talent in digitalization and in new energy. So I stop here. I hope that it gives you an overview of how Airbus sees the journey towards this Polar Star or 2050. Thank you.
Up here for. Thank you very much, Isabelle. There is a minute for maybe one question before we resume with the next presentation. Is there any? I don't see one right now, but maybe then I will ask a question related to the ducted and unducted. You were indicating the next program, and the question is about, is it going to be inducted? Is it going to be an unducted fan for the next single-aisle program? And I'm thinking about single source. Up to now, you were always at Airbus at least focusing on 2 engine suppliers. And if half of the community is going for one and the other half of the community is going for the other, meaning ducted or unducted, how do you foresee that to work?
So today what is very clear is that we are investigating. So a product is not existing without a clear outcome of what the technology is providing to us. So we have clearly indicated our wish to investigate on the unducted, which is a bit more revolutionary than the ducted one. And you know that we have started demonstration in this framework. The result at product level will highly depend on what we get. What is the gap that you have between unducted and ducted? What it means for the post-service? What is the business model that our engine manufacturer will have? So, of course, this trade-off is normal trade-off, but first we need to understand what the technology is capable to deliver.
Yeah, thank you very much. We'll come back to that, I'm sure, in the discussion at the end, because I think the question is the same for Terry, because I think that's a real question. I mean, Boeing has been working only with one engine supplier in this market, Airbus with 2, and if, again, one part of the community, of the engine community, is going with unducted, the other one with ducted, how to put that together intelligently. But a discussion for later. Now, coming to Thierry Beezhold. Thierry is Vice President of Engineering for Product Development. And before, he has a very, very strong engineering background as well, having been Chief Program Engineer for the market study, the NMA program study. Before that, he was Chief Program Engineer for the 777X. We may have a talk about the certification, which is imminent, and the aircraft is going to be in airline market very soon. So that's maybe also a question of what is coming next then when we speak about the long-range opportunities. And before that, he was involved in 787 development, certification, etc., etc. So a strong footprint, and his engineering history goes even back to DC-10 or KC-10, MD-11, 717. So Thierry, welcome, and looking forward to your speech. Thank you.
Well, good morning. It's an honor to be here, and I am looking forward to sharing a bit about our journey. And I think about talking about the future, it helps to reflect on the past. And, you know, we've been on this incredible journey now. And it really starts back, all the way back to Bill Boeing. You know, Bill Boeing just fell in love with flying and wanted to learn to fly, so what did he do? He went to learn to fly at Glenn Martin's school down in California. And he promptly bought his own personal airplane, a TA hydro airplane, and he brought it up to the Seattle area. And wouldn't you know, his good friend Herb Muster damaged it almost right away. And so it was the industry's first AOG. But Bill Boeing consulted with his good friend, George Conrad Westervelt, and they thought, you know, we could build something better and we can do it faster. So the idea of always innovating and always evolving started at the very beginning of our company's history. Then you fast forward about 35 years, Bill Allen, then the president of Boeing, took a group to the Farnborough Air Show, 1950, and they had been working on the swept wing, and felt like they had perfected some of the engineering that goes into that and podded engines. And they looked at the development of the Comet. They visited the factory at de Havilland, and they came back, and in 1954, they created what's shown there, the Boeing 367-80, known as the Dash 80. That airplane flew in 54, 2 years after the company committed the program. And it was a big gamble. They had no sold customers. It was intended as a demonstrator to prove out the capabilities of propulsion technology. It was 2 years later that the first 707, because the Dash 80 was really the forerunner of the 707 and also later the KC-135, but the first 707 entered service in 1958. Meanwhile, quietly, Douglas had been working on the DC-8, and they certified that airplane in 58, and it entered service in 59. But that was the beginning of the jet age. And really, it forms the baseline for everything that was to follow. Now, with the introduction of the jet age, it was all about how do we go farther? How do we go higher? How do we go faster? And I think that Breguet's range equation sums it up really well. There are really three levers to pull on. It's the specific fuel consumption of the engine, of course. It's trying to maximize your lift over drag at the sweet spot of a Mach number. And then it's the fuel volume. How much fuel can you take? How much fuel do you burn when you land? And it's all about weight. So these three elements really became the building blocks of where we've been over the last 75 years. It started on the propulsion side with the Whittle, the Whittle.1. That was an engine introduced. It was conceived back in the 20s by Frank Whittle and then went into production in the early 40s. Soon after that, turbojets entered the scene. Pratt & Whitney developed the JT4A, which actually powered those first 707s and DC-8s. But those were quickly replaced with the first generation turbofan. And they were relatively low bypass, but this was an engine now that was bringing greater efficiency to the market. It had an overall pressure ratio of about 16 to 1. So it was a pretty good advancement. But then the second generation of turbofans arrived when the 767 was developed, or the 47, or the DC-10, or the A300. These engines quickly brought increased performance. They brought pressure ratios on the order of 26 to 1, a big leap in technology. Then fast forward to the development of the 777. The GE90 now brought that up, the overall pressure ratio up to 40 to 1 with a large 123-inch diameter fan, 115,000 pounds of thrust. And then, of course, the 787 brought the Trent 1000 and the GE NX, raising the overall pressure ratio up to 50 to 1. And then, of course, with our 777X and our partnership with GE and their GE9X, which brings the overall pressure ratio up to 60 to 1 with a 134-inch fan diameter, a giant engine, actually less thrust than the GE90 because of the 777X's large wing. During that whole time, though, reliability was an issue at the beginning. It was problematic, but you see in this chart here where improvements were made to those early turbojets and turbofans. And then as the next generation of turbofans entered the market, a lot of the early issues were addressed. And if you look at the current generation of engine technologies, and while we do have issues, in comparison, they're extremely reliable machines. This all helped enable a significant improvement in efficiency. In 1953, the FAA incorporated the 60-minute rule. The piston engines at that time were becoming more reliable, and the idea for the 60-minute rule would allow twin-engine airplanes to fly 60 minutes outside of the diversionary airports. Now, improvements continue to be made. You can see here in the chart, the blue areas are those areas that were beyond the 60-minute rule. But in 1985, that was increased to 120 minutes because of the reliability of the aircraft and the propulsion systems. This enabled increased access of different point-to-point connections with twin-engine technology. And then, a mere 3 years later, that was increased to 180 minutes. Now, that was only achieved after about a year of stringent evaluation and testing of the reliability in situation there. But the 777 then went for early ETOPS, right? And because the reliability levels were increased so high that they're able to demonstrate right at certification 180 minutes. This opened up the world to long-distance, efficient twin-engine operation. The other level is aerodynamics, and the improvements over the decades, looking for greater efficiency in the airplane, largely driven around the wing. Now, the early conventional airfoils were pretty good, but with the introduction of the supercritical airfoil, several improvements were available to us. Probably the most important one is the weaker shock wave, providing less drag. Also, the shape of the wing could be optimized to allow a deeper rear spar, which actually provided a more structurally efficient wing box design. The 787, when we introduced composite materials, allowed us to do things in the wing design that previously we could not do with an aluminum airplane. Same with the 777X. When we designed that wing, we took all of the lessons from several iterations on 787 and continued to drive the efficiency of the wing. So when you look at the weight, the third lever, significant advancements have been made over the years from the 707 as we optimize the shape and the architecture of the wing using more advanced alloys. And then, of course, with the introduction of composite technology, we've been able to take that to yet another level. But, as you all know, there's no free lunch. Every program through development has been challenged with weight. Some of this is just a cause of the normal production process or development process, but there's also the increase of regulations, of requirements, certification requirements. Now, these are all actually good things because they improve the safety of the airplane. I think of nitrogen generation systems or reinforced bulkhead doors, secondary barriers, EME solutions, the way we size our ECS packs. I think about even the assumed weight per passenger. I guess we're all getting a little heavier, but all of these things drive weight into the airplane, and then the efforts that we have taken to take weight back out net out an overall improvement over time. So you have to look at all of these elements together, not in isolation. The integration between propulsion and wing design is key. The integration of propulsion, wing, and weight, also key. A good example is 777X. We evaluated the higher span wing, 235 inches. We added folding wingtips to keep it compatible in the current airports as a Code E airplane. So the weight increased, but overall delivered an improvement in aerodynamic efficiency. So when you step back and look at all of these integrated effects over time, the block fuel per seat since the 707 has steadily improved generation over generation. And you can see where the current aircraft models are setting new levels of performance expectation. I think Dr. Jim Heilman shared on Monday, the aircraft today use like 80% less fuel than those first generation jets. That's remarkable. You can also look at the integrated effects as productivity. If you think about seats times range divided by weight. Airplane family after family, generation after generation, has increased productivity over time. Now, if you went way back to 1930, it would take 10 days to go from London to Sydney with 32 stops. The 707 made a big jump forward and reduced that to 5 stops in 1.5 days. Today, you go direct. It's an incredible journey we've been on. But it's not just about payload range. It's also about noise. We have to solve for noise, generation after generation, always improving. This shows that where we've been from the 707, steadily reducing noise, being a good neighbor, and this is a key part of sustainability, continuing to drive down the noise of our commercial aircraft. But probably most important, and everybody spoke to this, is continuing to enhance and improve on safety. This data is just remarkable. When you look at the accident rate over time, over these decades, in a period where the air traffic has actually significantly increased, the record is impressive. The fatal accident rate, 68% reduced. That's denoted by the little triangles at the bottom there, in an environment where the departures in every decade continue to increase. Now, this is an area where we need to remain vigilant and continue to raise the bar. And so, when we think about all of these things that have been accomplished as an industry over the last many decades, and we think about the problems and challenges of sustainability in the future, I think this is one area where we've got to take a very clear-eyed look at how do we build and maintain this record of safety, efficiency that we've enjoyed over these last 75 years. I want to do a use case. We've been studying hydrogen-powered airplanes for a couple decades. And we've flown demonstrators of hydrogen cell and hydrogen combustion. But I just want to address 2 main principles of hydrogen that need to be solved to make this viable. Number 1 is just the volume. In order, when you think about a wide-body jet, let's say a 787-10, that has 336 passengers in a 2-class configuration and flies maybe 3,600 nautical miles. In order to produce the same amount of energy, you'd need to have a hydrogen tank that would basically be 78 feet long, significantly impacting the capacity of the airplane. This fundamental principles, and yeah, there are different ways you can architect that, different vehicle architectures that could potentially address that. But I think the other element that needs to be addressed are the fundamental properties of hydrogen. Hydrogen leaks more easily than some of the other alternatives. It can also diffuse into other materials, causing hydrogen embrittlement. But I think the most significant technical challenge before us is how do you have an airplane and ecosystem that is as safe or safer than what we have today when you look at the flammability properties of hydrogen compared to Jet A, which is similar to gasoline on the far right. Hydrogen gas is flammable over a much larger range than Jet A. And in the operating temperatures, hydrogen is more than an order of magnitude less than Jet A from an ignition standpoint. And it just brings me back to the development of the 787. This was in an environment where, in the wake of TW 800, SFAR 88, and the new regulations around flammability and ignition, I think of FAR 25981, that all rolled out right when we were developing the 787. And it took significant invention, development, innovation to be able to meet the demands with current Jet A aircraft on a composite wing. And to me, this is something that really deserves and needs to be solved here to make hydrogen-powered aircraft viable. So what's next? I mean, you think about where we've been, the journey of those 75 years. In propulsion, of course, yes, we are studying with all three engine manufacturers the current technologies that they have in their pipeline as we continue to drive efficiency out of the engine. We, in the aerodynamics, you know, the capabilities we now have with CFD, advanced computing, we can explore different architectures, different vehicle configurations that we've never been able to explore rapidly and iterate on to learn and then go demonstrate. A great example of that, of course, is the collaboration with NASA on the X-66 to explore the efficiency of a truss-braced wing. And then in weight, we continue to push the boundaries of advanced metal alloys and composites, leveraging the capability of an increased modulus fiber and how that can bring additional capabilities to the airplane. Now, this is really focused on the performance, payload range part of the equation, but another very important part of solving what's ahead is really the production of our future aircraft. Sustainability is a key component of production and end of life. You really need to take a full life cycle view of this. But as we've noted, you know, these machines are very complex, and a lot of our attention has also been on the engineering of our future production system. And how do we create a production system that yields a perfect copy every time, that minimizes defects, so that we can have consistency and much better quality of our products that get delivered. I think about the confined space that is involved in building an airplane or maintaining an airplane. That is a people issue. Being respectful of people, a core tenet, I think, of all the OEMs is, you know, how do we create a production system that don't put people in harm's way? The maintainability component in service is a huge lever in terms of the whole value proposition of the airplane. So how do we develop a vehicle that has lower maintenance cost, higher levels of reliability and availability? So when I step back and I think about the fundamental challenge before us in the area of sustainability, we have been on this remarkable journey over 75 years. I took time to go through that because it's important to realize where this industry has come. Always improving, never going back, never retreating, always improving. And any kind of change, whether it's to the vehicle or the infrastructure, must be made at a level of safety that is equal or better than the system that we have today. This, to me, is one of the biggest challenges that we have as a community. We should face into it and explore it and see how we can solve some of these fundamental technical issues that could enable significant change. And I think any kind of infrastructure requirements need to be taken into account, especially as we entertain alternate fuel sources. When you think about how prevalent the Jet A and SAF distribution systems are today and will be, and then introducing yet another system of production and deployment distribution is a monumental undertaking. The stakes are too high for us to consider anything other than a full life cycle view of what these changes require, from the initial extraction, development of an alternate fuel, distribution, consuming on the vehicle, and the end of life. All those elements need to be considered in total. It will clearly take better airplanes, cleaner fuels, and more efficient operations to meet the ambitious goals that we have. So with that, I will yield it back to Axel here and take any questions. Thank you.
Thank you very much, Terry, for that overview. Are there any immediate questions? There, please.
Thank you very much. I enjoyed both your lectures from Boeing and Airbus, and I would like to ask a question in principle to both of you. We've seen all the nice slides about ATAC that says we have to go in net zero in 2050. In a world where China and India are bringing more and more passengers, and we want to give them also the opportunities that we had. A significant part of the reduction CO2 comes from SAF, as is mentioned, but also from the new aircraft, from the technologies. We've talked about all the new technologies, which is very nice, but they come to deliver in new aircraft designs. Boeing and Airbus are working on successors for their A321neo and for the Boeing 737 MAX that will come in the market in 2030 and will fly for 20 or more years. So it's very important that these aircraft will contribute to the CO2 reduction for our environment. Now, the questions, of course, are what are the top level of requirements for these new aircraft? In design range, cruise Mach number, and passenger capacity. And an elephant in the room is, of course, the capacity of the airports, the limited capacity of the airports. And if you look at the busiest routes on the world, the distance they fly is less than 2,000 kilometers. We fly them with aircraft designed for 5,000 over 15,000 kilometers. If the capacity of the airports is limited, we start using wide-body aircraft designed for Mach 0.85 and long range on the short range. So my question is how Boeing and Airbus are looking at the top level of requirements of the new aircraft with the new technology that was developed in Clean Sky 1, Clean Sky 2, and has worked in clean aviation, to already in 2035 bring aircraft on the market that will be there till 2050 and bring a contribution, a significant contribution to the CO2 reduction in our world.
Yeah, thank you for the question. I would say it this way, that we have certainly, in Bob Pierce's talk, got at this a little bit before this session, about the whole ecosystem needs to be assessed, and the market for the urban mobility versus short range versus the longer range. And for us, you know, that's why we're active with WISC, understanding, you know, the urban mobility space, all the way up to the large wide-body, long-range aircraft. And I think you really do need to make sure we're thinking about what are the right vehicles for the right missions. We see a lot of wide-body or even narrow-body, long-range jets being used for short-range missions. So I think it does mean that you need a full portfolio of vehicles that are tailored for their mission to be a lot more efficient. Isabelle?
Well, maybe we keep that one for later for the big panel and focus currently on questions for Terry. Are there any other questions? We would have time for one more. Yes, there please.
Trevor Young, University of Limerick. Terry, thank you for a very informative presentation. I like the overall approach that you've adopted. My question goes more to a philosophical one, which you were alluding to in terms of safety and the significance of safety. And in my mind, it's absolutely vital in the discussion of how hydrogen is introduced and utilized on the airplane. In an ideal world, the scenario that you've outlined is spot on. You know, we cannot, as a society, afford any reduction in the safety of the aircraft. But we don't live in an ideal world. and we are going through a paradigm shift. And in some ways, we're going back to the 1950s in developing power plant for transportation, jet transportation. And at that time, when the industry was still learning very much how to design these things, operate these things, and safely get people to their destination, that the risks were higher. What if, this is the scenario that I'm painting, what if we find that these highly optimistic scenarios for SAF production are not fulfilled? What if we cannot, as a society, produce SAF in the volumes that we see on these wedge charts? What then? Does society not have to then look at the alternative, at hydrogen, and accept as a society that such risks need to be managed and considered? So can you comment on what I've just said?
Yeah, I do agree that we need to be looking for other alternatives beyond just SAF. Totally agree with that. All I'm saying is that we have to face into some of the very difficult technical challenges. With each one, there are lots of different options that could be explored, but each one we have to face into clear-eyed and address the fundamental technical challenges that potentially come with that. And until we do that basic foundational work, you know, that'll become a barrier if we don't solve those things in the coming years. Now, I agree, you learn by doing, so it's important to go demonstrate at scale, learn, and iterate. We feel the same way about the truss brace wing. That's a learning opportunity for us to validate the assumptions, our models, our predictions, and be able to use that data to iterate. I think the same holds true on alternative energy types.
Yeah, thank you. I think that's it for the moment. We're coming back to that. I'm sure we are coming back to that in the discussion later on, SAF versus H2. And maybe we should also explore the thinking, not just about 2050, but also what comes after 2060, maybe even 2070. It's beyond the targets which have been set, but that might be also a part where the benefits of hydrogen and the risks which are related to it might be mitigated and easier to be mitigated in a longer time frame for bigger aircraft with technology developments pursued. But that's definitely a discussion for later on. Now I'd like to move forward to two gentlemen and the companies they are representing who have been not on stage yet, EMBRAER and ATR. So starting with EMBRAER, with Cleiton Diniz Pereira da Silva e Silva, and he is Vice President of Engineering, Technology and Advanced Projects at EMBRAER. So he was very much involved in fly-by-wire technology development, in autopilot system development for the EIJ 190, 195 Phenom legacy, and also for this C390. Floor is yours. Thank you.
Alex, thank you for the introduction.
Axel.
Axel, sorry. Thanks for the introduction. And I would like to congratulate the ICAS for having the OEMs here. I think this is quite an innovation to bring the invited speakers from outside the research community to speak to this audience, and especially when we talk about sustainability, as this is an industry and a social challenge that we must overcome together. So it's very good to have the opportunity to be here speaking a little bit about our efforts and how we can collaborate more together. Just these years we are celebrating 55 years of existence at EMBRAER, and just a brief overview. We have 4 business units at EMBRAER: the commercial aviation, which designed the E-jets and has recently certified a new freighter aircraft derived from the U-1. We have also works on the executive aviation, where we have jets on the light jets, the Phenom 100, the Phenom 300, the Legacy, now called Praetor, and in the mid-size and super mid-size markets. We also have works on the defense side. C390, where I spent the most part of my career. I ended up as being the chief engineer of the C390. And the Super Tucano. And also we have works on service and support and trying to bring agnostic services to the company. So we are working mainly on the 3 segments and also services and support. And I will start, we mentioned this in the earlier presentation, that we need to attract talent. This challenge will not be solved without the right people, without the right background. And we are very proud at Embraer that we have a team of almost 3,700 engineers. And 40% of them with master's degree, doctoral degree, or specialization program. And over 800 patents. And how we do this, we have developed, and how can we bring this use of this engineering? I think we've been, in the last 20 years, working and certifying more than 20 aircraft. All of them bringing some innovation. I would mention the innovation in market as we designed the Phino 100 and the Phino 300 in early 2006. And then we have introduced the fly-by-wire on the Praetor aircraft, the Legacy 500, as it's called here. And then we designed the multi-mission C390 aircraft, a multi-mission aircraft that can do firefighting, aerial refueling, air transport, search and rescue, and other missions with very little time to reconfigure the aircraft. And in parallel, we were working also on the E-jets. So it was a great opportunity to develop the engineers because since 2000, we had several programs in parallel, and we could keep our workforce very, very up to speed, certifying and developing new products. But how can we keep developing talent? And this is something that I would like to share, is that since 2001, we have a specialization program at Embraer that is focused on a master degree, a professional master degree, in a different type. It has basically 3 phases. The first phase, the students learn the market, learn the operations, learn the top-level requirement of designing and building an aircraft. On the second phase, they specialize in each technical discipline, and in the third phase, we teach them together with engineers from Embraer, working side by side with them, how they could develop in an integrated way a new aircraft. And we are using this program from the beginning to teach the new technologies and put challenges that are needed for the sustainability effort. So some years ago, we asked the students to design a eVTOL. All challenges was them to design and trade off a hybrid electric and hydrogen-based aircraft. And when they get there to work with the team, they already know our process, and also they are familiar with the new technologies that we expect them to work with. And this was designed because we need, not only now, but in the future, people and engineers ready for the challenges. Recently, we designed a new effort. We have at Embraer 5 key initiatives or priorities to work, and we collaborated with ITA, Aeronautics Institute of Technology, and Brazilian funding agencies to put together an institute where we research together zero emissions, advanced design, and autonomous systems. All 3 linked to the challenge of sustainability. We are looking at new propulsion systems and how to integrate on the aircraft. We are also looking at new materials. And when we talk about autonomous system, we are also looking on new ways to reduce weight of the aircraft and how to optimize the operation. We have already 40 scholarships with doctoral degrees that have a research theme that was indicated by EMBRAER, and the researcher from the Aeronautical Institute of Technology and the one from EMBRAER work together, trying to develop tools, methods, and possibilities for the future. I spent some time speaking about the people, because we cannot change the future without the right people, without them knowing the problems, and without them knowing how we develop and design an aircraft. So these two initiatives are very critical for us to succeed in the future. Now going to the decarbonization. I think we saw this at least 3 times today. And I think we will see a 4th time. The challenge is very clear. The commitment of the industry is very clear. But the challenge is huge. And there is no one single solution. Even when we look and talk about SAF, Sustainable Aviation Fuel, we only produce less than 1% of the required Sustainable Aviation Fuel. So there are a lot of challenges there too. When we speak about new technologies, as we already spoke several times today, in aviation, safety first, quality always. So any new technology that we are going to insert in a new aircraft needs to be very well matured before we integrate it on the aircraft. And depending on the size of the aircraft, the solution may be different. If you have a small aircraft, we may use electrically powered aircraft vehicles, battery, as we are doing in the eVTOLs, as I'm going to show later. Although the challenge is huge, we are fully committed to pursue this goal. And again, I think it will not be one competitor. It will be not only the industry. We will need the entire ecosystem to solve this issue. The technology alone is only one piece. We have to build the infrastructure, and we have to make the technology at the right price in order to have a viable product that satisfies social needs. So, now let me talk about our roadmap, what we're studying. Today, I will talk a little bit about what we have on the commercial aviation, that is the E2. As we've seen in previous presentation, we are progressing, and as industry, we are getting better than our previous products generation after generation. That's the case of E2 that I'm going to show you later. We are also working on the eVTOL. We, as Eve, are designing a eVTOL, and I am going to show about the technologies, the main challenges that we are facing on this development. We've done some demonstrators in the past with Ipanema. Ipanema is our agricultural aircraft that we flew with 100% electric in 2021. Later I'm going to talk about SAF. We are fully committed to delivering an aircraft 100% compatible with SAF by 2030. And I will talk about our 3 future concepts that we are working. And by saying concepts, we haven't yet launched those programs. They are technology efforts that were designed to focus the key technologies. And I will say some words about how we are working with these concepts and how we are trading off technologies for them. And we foresee later in the future, maybe after 2050, the E2 size aircraft powered by hydrogen. As I said, we saw before, we are progressing as industry. Generation after generation, we are producing better and more efficient aircraft. In case of the E2, which has an aspect ratio of more than 11.7, and that's a advanced metallic wing, with new engines and the 4th generation fiber wire, we were already able to reduce the fuel burn per seat in 25%. If we look at the E2 horizontal tail, the 195 E2 horizontal tail, it is almost of the same time, the same size of the half of the size of the previous generation E1. We did this using the advanced fly-by-wire that we learned in our past programs. So here, we will keep progressing and studying advanced materials and also new ways to design the wing in order to produce a structural and aerodynamical efficient aircraft, but we will also need to have new propulsion systems that can reduce emissions. When we talk about the urban air mobility for small range, the vehicle that we are designing is for 60 miles range. For this kind of vehicle, the fully electric solution or fully electric architecture seems to be a good choice. But for this type of aircraft, the challenges are huge. We have to figure out certification requirements, operational requirements. There is an infrastructure to build. There is an air traffic management that needs to be built. All the stuff that we also saw in previous presentations. But there is the specific energy density of the batteries and also their life and their associated costs. It's quite challenging with 200 watts per hour per kilogram to design an aircraft that can take off and land vertically. So a lot of work needs to be done also on improving battery specific energy and also life. We have been researching battery by our own, and we have some collaborations with institutes over Brazil. We have been studying how we can improve the life and how can we increase the specific energy of batteries. But this is something that we could work more together. I will not go through all of this, but I would like just to point out that since 2005, we have flown with Ipanema. It's certified to be flown with ethanol. In Brazil, I don't know if you all know, but cars can be fueled with ethanol since 1979, I guess. And it's certified and be operated, and we are fully committed to advance it in certifying SAF by 2030 to have all our aircrafts operating with SAF. And here the challenges may be not only on the technology, it will be hardly on the infrastructure and the economics. Today, SAF costs more than 3 or 5 times more than conventional fuel, so we need to work on the infrastructure to produce more and also to make it more economically viable. And starting to talk about the concepts that, as I said before, are not fully launched program, but are ways that we decided to work internally to develop the technology. We are not just developing the technology, we are talking actively with possible customers and identifying their needs and market opportunities. That's why we've been changing and evolving the concepts through the years. And we talk to the customers and try to identify the value proposition of each aircraft, and we identify with suppliers, research institutes, technology states, and try to come out with the project that would satisfy that need in the horizon that we need to be fully committed to the decarbonization by 2050. The approach is set-based design, so we try to study all the possibilities the maximum time that we can to really learn everything that we can from that combination. And talk about our Energia family, the 50-seaters. We have three concepts under study. The Energia hybrid electric, that is for 600 nautical miles. And you will see here that we put the reduction in CO2 for 250 nautical miles, because our research shows that more than 80% of the flights are for short rows, 250 nautical miles. And we see that it can provide a reduction of 25% of CO2 emissions if it uses Jet A, and up to 90% using SAF. And I will speak a little bit more about it, because it has, as we believe, a more mature technology to be developed into a product. The second concept is the Energia fuel cell, also with a range of 600 nautical miles. And as we are using hydrogen, it reduces 100% the CO2 emission. And the last one, the Energia hydrogen dual fuel cell, we are studying to have an engine that can be fueled both with Jet A and hydrogen. Well, talking a little bit more about the hybrid electric, I will not spend so much time talking about the advanced aerodynamics and weight, because the plan is to bring all of what we learned in our previous jets in aerodynamic design and structural design, and improve the aerodynamics of this aircraft and the structural efficiency of the aircraft, using also what we've learned with the fly-by-wire technology to improve and to the performance of the aircraft. But we have chosen rear-mounted engines for noise reduction also. And our concept is to have a thermal engine, a next-generation thermal engine, that is complemented in higher demand phases with a battery, a small battery, 550 kilowatt hour. This is almost the same size of the battery of a small BOID Dolphin, that will provide extra power only during taxi, takeoff, and climb, and also that could be used for providing extra power to, for example, the electric de-icing system. So we are also studying more electric systems that could be used on this aircraft in order to improve fuel burn. Here is just a more detailed information about this architecture that we chose. It's a thermal engine that has in parallel an electric motor. And every time there is extra energy from the system, we can use to generate more electrical energy and to power or to charge the battery. I will not go through all the details, but in summary, the thermal engine is optimizing for cruise. We optimize the thermal engine for cruise and for taxiing in and out, takeoff and climb. You use extra power from the electric motor. And in case we need for de-icing, for example, we also can use the electric motor. And why we did this? Why we chose this architecture? Because small batteries are prone to be available and could already bring a reduction of up to 25% of CO2 emissions with this architecture. The other architecture that we've chose, or we are studying, that we think we can have technology readiness by 2035, is the Energia fuel cell, where we use, you saw that in the electric, you use small motors. Here we use a 2.5 megawatt electric motor it has a higher weight. It weighs more. The wing of this aircraft must be higher than the one increased from the one electric or the improved gas turbine. There are challenges on the thermal management, and I will just share that what we've been trading off is to have a small air inlet in the vertical tail that helps a lot on the thermal management. If we have 5 megawatt of engines installed, we are producing almost the same amount of heat in the aircraft. So the challenge here is how can we, besides all the challenges with hydrogen, how to store efficiently, how to maintain the systems very safe, we also need to take care of how we manage the temperature of the system installed, and that's why we are studying that air intake on the vertical tail. And the last one, more challenging, more in the future. How can we cope with the heavy weight or the volume of hydrogen? What we are thinking is that we should optimize the hydrogen just for the small routes. If more than 80% of the routes are for 250 nautical miles, the hydrogen tanks and systems should be optimized for those missions, and we could use the wings with jet or SAF when needed to have a longer flight. So we could, in this way, anticipate the entry into service of an aircraft like this. But we are looking for feasible solution. That's why in each concept we are trying to just introduce the technology as needed. And the challenges are not just technical, as we mentioned before. It's also infrastructure and also economic. We need to have the right technology at the right price to have a product that the society can use for their benefit. And that's it.
Thank you, Cleiton. Also here we have time for 1 or 2 questions before we go to the next speaker. Yes, please, there.
Trevor Young, University of Limerick. Thank you for a very informative presentation this morning, and in particular I enjoyed the discussion on the presentation on the Energia. It's very exciting. My question goes to your wedge plot, which you showed right at the beginning, or what some people at this conference have called the lasagna plot, in which you've showed the contribution of the various technologies towards net zero by 2050. Now, I noted that your assumption there is that over 70% will come from SAF, which is considerably higher than what we've seen earlier this week, where the figures have been around about 55%. So my question to you is this: in establishing that scenario, that plot that you've shown, did you actually look at what SAF contribution could realistically be in the future, considering price availability, or did you simply assume that it will be available and treat the SAF contribution as a variable in order to get to net zero by 2050?
I think in the ATAG report we have several scenarios. This is just one of the scenarios that is already on the ATAG report that relies more on SAF, and we are conveying that vision that we think, especially because we have long cycle products that are already flying, that we will for some time rely on SAF. And we recognize that there is a huge challenge because less than 1% of the SAF that is needed is produced today. So it will be a huge challenge. And we're already seeing, even in Brazil, we have huge investments now from the government, and even EMBRAER is partnering with several possible suppliers to develop SAF. It's a huge challenge, but I think it will, as the infrastructure is already there, and if we can produce drop-in SAFs, we could bring the technology and just overcome the economic one and not having to cope with the infrastructure one.
Thank you for your answer. Thank you.
Yeah, there is a question here, please.
Hello, Vincent Foucault from Clean Aviation. A question about your energy concepts demonstration plan. So do you have any plan for ground and flight demonstrations around those concepts?
Not yet. We are on our conceptual studies trying to finalize. We still have some iterations with potential customers trying to capture the requirements, the top-level requirements. You saw that we have made assumptions to optimize the CO2 zero emission for 250 nautical miles, because this may seem to be a true need from their prospective customers. And this also brings the possible aircraft much sooner in time, because we can implement it much sooner in time. But no plans yet to flight demonstrate or ground demonstrate them.
Yeah, there is a question. Maybe the last one before we then go to the next presenter.
Hi, Lorenzo Mazzai, Ergon Research. I have a question about the dual fuel engine. Since we are working in a Horizon Europe project called HOPE, where we are designing a multi-fuel combustion system capable of burning both kerosene and hydrogen, I was wondering if you are already talking with some aero engine manufacturers, because in my understanding only Rolls-Royce, I think, is publicly working on that in Cavendish or another clean aviation projects.
We are part of the Cavendish project with the Rolls-Royce, and we are studying there.
Okay, thank you very much. Also an interesting topic maybe for the coming up discussion. I have a couple of important questions, but I'm sure that you have even more. So let's look forward to the final 30 minutes at the end. But now I'd like to hand over to Daniel Cuchet from ATR. Daniel is the technical director and the head of the design office of ATR, and previously he was the chief engineer of ATR, and I understood that before you were also involved in drones and the Airbus MRTT work in your previous technical life. So please, the floor is yours.
Thank you, Axel. Good morning. So I will try to explain to you all the topics we need to tackle at ATR. So first, to remind quickly what is an ATR aircraft and what is the company. And second, to guide you under our duty and our commercial strategy related to sustainability. You need to understand, starting from the regional aircraft where we are working, it's quite a different area from the single aisle or, of course, wide body. Our customers are different, and you will see. But first, who we are, in a nutshell, we are a sister company of Airbus and Leonardo, 40 years of aircraft delivery, and we have delivered 1,700 aircraft this August. Backlog interesting, and 2 billion people transported. We are the only turboprop aircraft in the regional market since a while now. And Axel, to answer to your question, yes, we try to maintain the 99%, but of course, competitors will be always welcome. So what is our, in a nutshell, customers? They are very different. We have very small airlines who are owning one aircraft or two aircraft, and we have big ones like Indigo, Azul, Air New Zealand, the JAL Group, Japan Airlines, who are owning 50 and more ATRs. So very scattered, and you need to understand that the ATR is sometimes a very small single aisle. So considered as the last 200 to 300 nautical mile transportation for 70 class passengers, but also it shall be considered as a four-wheel drive where, for example, in Asia and Asia Pacific, the regions that we are working with are very different, island to island, very remote areas where sometimes the runway is in gravels. And so this is a very different way of the single aisle, of course. And this is driving a lot, and this is for me important for me to guide you. This is driving the sustainability approach. We cannot consider that all customers that we have at ATR, and more generally the regional market, will be tackled all equals. The big airlines will act differently versus the sustainability compared to the small airlines. In Europe, for example, which is quite motivated by the sustainability or the CO2 emissions, we are growing, but we could grow in a faster way with some cultural change. Sometimes in some remote areas in Europe, we have a load factor of the aircraft with old aircraft, and I think my colleagues presented the evolutions of the aircraft since quite 2 or 3 decades. We have old aircraft still used, which are not efficient. And if, as of today, we jump into new aircraft, and when the load factor allows it to do 70 passenger class, we could reduce by almost half of the CO2 emissions as of today with the current ATR and turboprop aircraft. The turboprop, of course, I don't need to guide you. The turboprop is for low speed, a very good and best efficiency aircraft. For higher speed and long range, of course, it's not optimized at all. And our core market is related to this 300 nautical mile and 70 pax. So we could do better if the culture of speed is different and if the load factor, of course, is adapted. We are not here to discuss higher class jets like 100 seats or even high-speed single aisle. It's not our core market. 2 to 3 examples. In the worldwide airports, 1/3 are served only by turboprops. And 40% of passengers of the ATR are serving essential services. So here you understand that the answer of the sustainability for ATR and more generally for the turboprop market is different from only tackling the efficiency, only tackling the economical things. What is our product strategy? And I think you will understand quite clearly where do we want to go. First, at short term, it's clearly to enhance the ATR as of today. I will come back to that, but it's clearly to tackle 30-seaters market with adaptation of cabin in particular. To enhance high-speed internet connectivity. We have done very recently a very good improvement on that. So this is today. I will not spend too much time. Tomorrow, it's to adapt our product to the needs. Tomorrow is, for me, 27, 28 timeframe. Tackling new front door, 50 seats on our ATR 72 with a new cabin setup for high-end markets, especially US, North America, and Asia. And of course, working on the 100% SAF. And on the long term, so we are discussing here 2030 plus. You need to translate it at probably 2032 timeframe. We need, and I will jump into the EVO, which is the new ATR that we are developing. which is related to a mild hybrid propulsion. We'll not spend too much time on the cabin. This is what we have and what we want to target. No, I will not show the same attack picture, but it's roughly the same idea, Cleiton, I agree with you. It's to say we have operations, ATM, technology, and SAF. I don't put the percentage because all along the week, Axel, I think we have seen that all percentages are different. So as of today, as I said, today if you take more generally a turboprop, in particular on ATR, which is the only produced, but more or less a turboprop, you can divide more or less by 2 the CO2 emissions. This is due to the efficiency of the aircraft. It's not by chance, it was evolving, but more or less, this is the technology already. Again, not adaptable to all circumstances. Small spot points, 300, 400 nautical miles, not more, and low speed. Already today, if you replace one regional jet, which is an old one, let me take old ones as the best explanation. More or less, an ATR is 23 tons of max takeoff weight. We still have jets which are flying with the same class of passengers, 2 times more max takeoff weight. Of course, it's not optimized, so we can reduce by 4,400 tons per aircraft per year if we replace this as of today. You can read it, and of course, the fact that we don't do contrails. Just a few minutes to discuss about the flight ban. Of course, it's an interesting discussion, but the high-speed trains that we have in Europe, for example, where we are in the overall aircraft and aerospace companies and airlines put in competition, are for me not relevant. We are not addressing the same type of market than the high-speed trains. So for me to compare apples and oranges makes no sense. We are not doing the same things. Infrastructure are fully different. Number of passengers are fully different. So I think it's not relevant to, for example, to close one route if it's adapted to some particular passengers. But of course, if we are in competition with a high-speed train from, let's call it, from Bordeaux to Paris, if there is something which is in place and working well, why not? So technology roadmap. 3 steps. One is already done. This is on the right, the improvement we have made with our partner engine manufacturer Pratt, which was delivered end of 22. This is an evolution of the current engine story. It's providing -3%. I will come back to that. On CO2 emissions, it's quite an improvement, but it was an evolution, not a revolution, as Isabelle said. Second topic, SAF. I will not enter into details. I think my colleagues already did. Here, we are linked to the ASTM certification, and I think I have not heard too much this week about this limitation. I think the aircraft manufacturers are quite ready to work on SAF, but they need to be supported by the SAF manufacturers and additives manufacturers, which I don't see quite motivated. I think it's an interesting topic maybe for the roundtable that we could have, despite the fact that, and I agree with my former colleagues, the production is not at the level that we want. And third topic for the decarbonizing, this is of course the EVO. So you see here the -20%. I will jump into details because we want to target more than 20% CO2 emissions with additional features. First topic, may I ask you to look on the gearbox which is on your left. It's really used for the potential improvement that we will have for the hybrid propulsion. So this gearbox is really something which is very interesting for the evolutions we want to put on the Evo. But first, the aim of this improved engine was first to reduce the maintenance cost, to reduce a bit the specific fuel consumptions. It's done, and it's in service since quite a while. The airlines are quite happy, not seeing only 3% of fuel burns, but more. SAF, we were the first aircraft in 22 to fly on both engines with non-drop-in. It was with a full commercial and delivered aircraft with Bratans. It was without additives, and it was a non-event. Since a while, we are working, of course, with all the authorities, and especially the ASTM. I have put in terms of time frame ASTM relevant because here we are, I think, limited. I think all the aircraft manufacturers are motivated to modify their aircraft, gauging, weighting, and so on. But I think we need here to push a little bit. And now a bit of trade-offs that we made in ATR and within the mother companies about what could be the evolution of the ATR in the future and jumping into the Evo. So the first line, you see the reference, which is the datum, the ATR 72600. 72 packs, more or less 200 nautical miles of average mission. And just below, you see the all-electric, meaning with batteries. I have put mission in terms of range. The below 10 packs, it's far below because we are not sure that we even can put some passengers here. So more suitable for very small modules. We were discussing, and I agree with you, Cleiton, the batteries in terms of density energy is difficult. For an ATR, the class is above what we can accept. So this is not a good solution. Reminding you have on your top right, an aircraft like an ATR or turboprop in this class is around 4 megawatts of peak power. Second solution that we have tackled is the hybrid solution. So you keep your engine or the type of engine, the thermal engine, and you add electrical motors. I will not go into details now, but this is a principle of parallel architecture. This is for us the best trade-offs, not only technical, but also for our customers. And third solution, we discuss a lot about hydrogen. Yes, hydrogen could be also a solution for this class of aircraft, but we think that it's a very long-term solution. Probably it will impose a lot of modifications to an existing aircraft like we have. So this was also seen as potential for our mother company to work on, and Isabelle explained about the AIRBUS strategy. So if one day the hydrogen is ready, safe for a class of ATR, maybe we will include it, but for the moment this is not the strategy. The strategy is in the middle for the hybrid solution. Again, come back to our customers. Our customers are very different, and to put hydrogen to all our customers could be a big mistake. We have customers, and I see customers with very small fleet. They are very remote. I have customers who are in Papua New Guinea. I have customers in Tahiti, in the Pacific Ocean. If I provide them an aircraft which is fully hydrogen, it will not tackle their needs. And they will tell me, Daniel, I think you missed the design of your aircraft. So this is what also we need to take into account. That means not only discussing the, let me say, European way or North American way in terms of sustainability, but also the overall global view that the aircraft shall do. It's a mission, it's an overall mission. So to answer with only one solution is not appropriate. So what is the Evo? So the first aim is, of course, to reduce CO2 emissions and to do adaptations and enhancement. The main announcement is, of course, dedicated to the propulsion system. Again, with an hybrid solution. I will come back to that more after. The first aim was minus 20%, and we are today discussing with the Clean Aviation team, with Axel's team, to even improve this. The minus 20 will be given mainly by the propulsion system. Let me say like that: a new engine, a new thermal engine, to make it clear, and an electrical motors plus the batteries. And we want to go more on some enhancement. We'll jump into the maintenance cost very rapidly. We need also to decrease our maintenance cost to keep the aircraft economically viable. Entry into service, I already explained. So we need to be more sustainable, but we need to be also more profitable. A very good aircraft shall be sold to companies to make also money. So we need to be clear on that. So I suggest that we go quickly. I already explained all this. And more jumping into some techniques. So 4 megawatts of electrical equivalent energy. What we target, it's clearly to have an hybrid, what we call the mild hybridization. So mild meaning moderate, but being able to enhance the mild hybridization from the first entry into service, and maybe when the batteries will become, if one day the batteries are becoming more efficient, to jump into this more efficiency. But to have the architecture, the electrical motor, and the possibility to improve the hybridization. So we are discussing about a power split of around 20%, which is big. We are discussing 500 kilowatts of peak energy. And as you see on the left side, you have the battery pack driving and distributing the electrical power. So it's quite a simple scheme. I can tell you that doing the integration and the modification of that, it's quite a challenge. In terms of missions, where can we use it? The main aim is, of course, to reduce a little bit the size of the engine. I want to make clear that mild hybridization shall afford something. So it has to pay the payload it's done for. And for me, this mild hybridization shall be here to also reduce the thermal size of the engine, to be able, when we have the need, to help this thermal engine. You see that we target two main points. In fact, the two main points of usage during the mission are the ones related to the max power that we ask on our engine. The max power of the engine is designed on the takeoff, of course, and the top of climb. All the rest of the mission is with lower energy demand. The cruise, of course, and all the rest. So we need to downsize the level of the thermal machine to be able to be used in parallel of the electrical motors. And this is what you see here in sequence. So that means during takeoff and top of climb, we use the electrical energy that you have recharged on ground to be more sustainable. So this is helping the engine. And for the rest, you can recharge on flight, but of course, it's not a free lunch. We will consume some energy. Let me jump into two projects that we are working on. So you know that the regional market and in parallel the turboprop is of course the first big step in terms of sustainability, where we can do something. We can bring, and there is a lot of development, be it in hybridization, be it in hydrogen, be it in a lot of other technologies. And two projects are really supporting us. First in France, this is what we call the CORAC. So this is a research organization called by the GIFAS. And we are developing with this financial situation, we are developing a concept and we are supported by. The second one, and this is where I think it's quite a very good opportunity. We are supported by the Clean Aviation program, which is quite important for us. The Clean Aviation makes concrete things and put effort and is forcing the OEMs like us to have concrete results and not only R&D. So this is where we are today. So we are part of the Clean Aviation phase 1, which is developing the concept of new aircraft, in particular the regional, but not only. It's discussing SMR and the rest of the technologies. So we are now part of the technical committee, and the EVO could be part of this maturation. And the big challenge the SRIA has put to us is clearly to say the -20, it's good. It's quite very good in terms of reduction, but you need to go more. You need to go more to -30%. The -20 will be given by the new propulsion system, and we want to work on this rest of 10% to jump to the -30% on, for example, wing adaptation. You know that the ATR is quite a very robust and safe aircraft, but the wing is to be optimized and can be optimized in terms of profile and airfoil, and the rest in terms of aero adaptations and so on. So this is what we are working on and will be working on. So to make it clear on the regional aviation and the ATR, today an ATR is already very super efficient compared to other old aircraft. Let me say old aircraft. So this is to be tackled because I'm meeting a lot of governmental people and from many countries. Sometimes it's not understood that as of today, if you want to replace an old aircraft by a turboprop, not only an ATR but a turboprop, you gain money and you gain CO2 emissions. But we need to develop again and do a new step. And this is, of course, the SAF. No question, we need to work on it. For me, SAF is a good intermediate solution. I think it's important to do it, but it will not be the end of the story by far. So it's a good intermediate one. And we discussed, and I think my colleagues explained the challenges of the supply and the cost. I will not come back to that. The ATR EVO, of course, is our strategy for the long term. Mild hybridization, and again, to come back to the -20 and -30, we can do more probably, but we start from half of old aircraft. So already to gain this, it's quite a lot of challenge. And this is done. I think, Axel, I'm quite in time. So thanks for listening, and I'm ready for questions and or for panel discussions. Thank you.
Yeah. Thank you very much, Daniel. We have time for maybe one question before we go to the bigger discussion round. Are there any requirements for answers? I see here is a gentleman.
Thank you, Daniel, for the presentation. A question about the infrastructure. You've been very clear about the hydrogen challenge for small operators. What about battery charging in those countries, small operators?
No, clear the infrastructure, and I think Terry mentioned the infrastructure importance. It's quite key. On hydrogen, I will not come back to that. Some will be equipped, some will never be equipped with that. Okay. In terms of batteries, I think the challenge is less important. When we discuss this type of battery class, we are discussing more or less about electrical chargers which are used for cars, for example. This is the same class of charging energy. So these kind of things are more easily installable in remote countries, or if there is nothing, the versatility that I mentioned is quite important. So that means you are not obliged to have it, but it's better in terms of CO2 emissions if you have it. But you can do base to base, and if some bays are not equipped with this kind of chargers, okay, that's not a drama, you can still use the aircraft. I think the versatility of our aircraft is quite an important challenge to keep at our customer and airline level.
Yeah, thank you. Is there any other question? No? I think then let's move into the bigger round, and let's take Isabelle, Terry, and Cleiton on board as well. And if you please take a seat over there.
Yep.
So I think we can switch on the light if possible, so that we can see the audience better. It's quite dark out there. And I would like to, please take a seat, and I would like then to open the round for the first question. Who wants to be first? I still can't see anything, so you need to shout or wave, or can we please switch on the light? Yeah, much better. Thank you. Is there any immediate question? Does not. There's one.
Hi, again, Lorenzo Mazzai, Ergon Research. Maybe a question more for Airbus, but also for the other manufacturers. Airbus is known to have a multiple engine option, let's say, the Geared turbofan and the LEAP and so on. These new engines that we are seeing are becoming a bit different, meaning them not only ducted or unducted, but also if we keep the ducted configuration like the UltraFan or the wet engine, the behavior, the concept is extremely different due to the water recycling in the wet engine, for example. Will Airbus be able to provide this multiple engine option also in the future?
I think that answering that question is more the end of the story than the start. And of course, in an overall strategy, once we will talk about new single aisle with new engine options, the industrial configuration of our supply chain is part of the story. However, and I answered already to Axel previously, we need to understand what this technology is about and who is the part of the supply chain is capable to follow us in that investigation. So we are partnering and we are discussing with the engine manufacturer over the world on the various concepts on which they are also wishing to invest, because it's not only, I would say, Airbus wish. We have a momentum, we are capable to drive some innovation, but we need to be followed. First, it needs to make a demonstration, understand what this technology has to tell us, and then we will discuss about industrial strategy.
Yeah, and maybe I can just add too, I totally agree with that. You know, some of these emergent technologies are compelling, but they need to be demonstrated and to understand, you know, the value that they potentially bring. And as I mentioned, it's important to gauge that value at an integrated total effect. An engine by itself can claim some pretty impressive performance capability, but you need to understand the total integrated effect on the airplane. You know, the wet engine, for example. I mean, that's another system. They have to integrate into the airplane. So you gotta, it's not good or bad, it's just you gotta take that into account to understand what the potential benefit could ultimately be. And as we learn, you know, then then we start exploring those in more serious detail.
Yeah, thank you. Anyone to compliment? No? Then maybe to the next question. There is one, please.
Thank you, Axel. Ron van Manen, Dutch National Innovation Program. I'm interested in going a little bit further into the question that Fred Abink asked, but that was during Terry's presentation. And I think, Terry, you gave a partial answer to that, and I remember Fred also requesting a response from Airbus. I hear in terms of next generation single aisle, and I think we see, if you look at the next generation of long-range aircraft, a lot of one-to-one replacement. And fleet flexibility, the airline point of view, in my view, has always had a very large impact in terms of going for the longest range, highest capacity among the customer set, maybe even disproportionately to the launch customers. And then you look at operations, and 80 or 90% of operations of the fleet tend to be at a lower pax number, but particularly at at a lower range. And so there's a certain level of overspecification. And while I understand the idea of standardizing, looking at a 50,000 plus fleet in 2050, is there some way in which we can get the low-hanging fruit of aircraft being specified for a shorter distance, a higher capacity, lower and slower? We heard that a number of times during this conference. And is there a business case around that? So that was my contribution to what I think Fred was also pointing at.
Who wants to start? Isabelle, please go ahead.
Yes, so your question is what is the product positioning, basically? So, and does that help in the carbon contribution? I think that you always have these axes in aircraft and product positioning, you know, the cost per seat and the cost per trip. This is an important part, and you see that where our product, if you draw a line, you will see that we try to optimize, because it's also the fear factor that you have when you have a large aircraft, which is designed for short range, and you need to understand which market is addressed and how many aircraft is there. So there is not only, I would say, the optimization or the pure theoretical part of having volumes, there is what is operating actually and operated actually on the market. And today we still have, I would say, something which is, I don't say that it's conventional. We need to look at the versatility of our fleet in the lower end market. But I would say it is not an obvious, I would say, journey to increase, I would say, the size with a very small range in terms of aircraft optimization. However, we have a fleet, to be honest, we have a fleet which is super versatile. So if you look at the single-aisle market, we are doing very short range to up to the lower end of the long range. And we have 330neo, which is super versatile also, which is used for, I would say, medium range to long range. And then you have the upper range. So it's more a question of family positioning.
Anything to add, Terry?
No, I agree. And you know, as I said earlier, you really need to look at where, you know, the whole ecosystem is headed, and always be rethinking about from the products that serve all those different markets, how they may need to evolve. While, you know, in the single aisle space, we have very capable aircraft today, and will so even more tomorrow, capable still, however, of long range. They're not designed or optimized for the short range mission, which I think is your question. And is there a market space that would allow for such a product to be successful? Because that is a different airplane with different capabilities than what we typically design for the longer range mission, to give that flexibility to the customers. So I think it's a great question, and I think as we see how the whole commercial transport ecosystem evolves, you know, there'll be space for different product decisions out there ahead of us.
Yeah, there in the middle there's a question.
Maybe waiting for the question. What you are both proposing is more or less to have a big regional aircraft, be it jet or prop is not the issue, but to design a big regional aircraft, so to do 500 or 600 as a point of design, it will be quite a challenge in terms of economics. Because this aircraft will be designed for only that, not capable to do more in terms of mission duration. So the economics here will be quite a challenge, and you need to be sure that the airlines and the passengers will be here. So that's quite an economical challenge, not easy to answer.
Okay, to the next question, please.
So Naomi Allen, Royal Aeronautical Society. There was a mention of hybrid hydrogen, and it just made me wonder, for the larger aircraft, given the challenges that are going to be associated with hydrogen infrastructure, and that's likely to take quite a long time to come in, do you see the potential for an interim solution of a larger aircraft which is able to operate on both SAF and hydrogen, or is the performance likely to be too compromised by the necessity of having duplicate systems for it to be an attractive sort of economic solution?
So, again, here, maybe I'm repeating myself, but I think that the important thing is to have a target, to get there and to work, and so it drives the right question. And there is a lot of question around the hydrogen-powered aircraft, which first needs to be answered. So, hybridization versus another, I would say, fuel system for higher end, I would say, application is potentially a second question that will come. Your question is about upscaling the hydrogen. Our first target is to be capable to propose a commercial type aircraft, hydrogen-based, with all the challenges that we have heard around the table, because we have all, I would say, not only a technical opinion, but we need to mature this technology, answering to the safety part, demonstrating its capability to operate, etc. So upscaling will be a second round.
Yes, there is a question, and then
I will
in the middle.
Fred Abbink from the Netherlands. I come back to what Ron van Manen said. When you studied the Boeing NASA studies on sugar, they started, the optimum speed was 0.7. That was their starting point. When you look at the ascent studies from FAA, they said 0.7 is for the short, medium range, the starting point. They have their Project 10 and Project 64. They look at what can you gain when you make the range shorter, and what can you make with speed lower, because you have this snowball effect. Well, I've been very lucky to be participating in Clean Sky 1 and Clean Sky 2, and there the European Union said our objective is to reduce fuel burn. The industry says our objective is to have better customer value and market. And somewhere we have to find an intermediate, because at the end of the day, the environment will be very important. And if we say the fuel price for hydrogen, electrical produced with solar, electrical, hydrogen, SAF, if we have that, the price, that might be maybe 5 to 10 times higher than what we have today. And if that parameter is used in your direct operating cost, maybe the design will be, you'll be more favorable, the design, to have a shorter range, to have the design range and the operational range fit better than they do today, where you have maximum flexibility. The maximum flexibility is important, but can we afford to have this maximum flexibility between the long range and the short range operation?
Yeah, I think it was less a question, but a comment. But I think the lady and gentleman have dwelt on that already. But I think it's a very valid point, and maybe that's something we need to think about. I think we need to change our conventional thinking and think about what is the target. And I would like to come back in a second, but maybe we hear first the question of the gentleman there in the middle, please.
Thank you very much for your presentations. Very enlightening. A question, though, for the the selection, for the panel. The way I see the market right now, it is primed for disruption. It's not a case of sustainability versus technology versus society. There will be somebody who comes in and fundamentally disrupts us. No longer a tube and wing, blended wing body as an example. I'd like to hear your thoughts on disruption at the macro level, whether we should be embracing China into the mix, whether the likes of ATR should be getting a step up into the large aircraft platform zone, and whether there should actually be, and this is more controversial, an inhibit on competition, an inhibit on mergers and acquisition to promote competition on a sustainability level rather than just a market dynamic level.
Well, I'll take a cut at it and then pass it along here. In terms of disruptors, of course, you know, we're always evaluating all the alternatives, the more conventional or the very extreme disruptor approach, to always gauge, because you got to always be paranoid that one of these things comes along, and if you're wrong, that's not a good day. So we're always evaluating that, and at least on the Boeing side, we're always looking at what are the capabilities. I mean, it's managing risk, technical viability, to be able to deliver on our commitment to net zero by 2050. And so we're always evolving that in our work that we do, thinking about the next generation of aircraft. And if something comes along, I mean, frankly, that's why we've committed to the X-66 program. I mean, that is, yes, it's a constant section fuselage vehicle arrangement, but that approach, if it can deliver on the aerodynamic benefits, it can significantly change and be a disruptor in of itself. Maybe it's not as some of the other concepts out there, but so we are always exploring those things to see what is the right balanced compromise of capabilities that, as I said in my talk, is always moving us forward and not compromising on things, whether it be safety or sustainability. Every parameter, we got to continue to move the ball down the field and not compromise, especially on safety. That's got to be fundamental in any kind of new energy carrier that we look at, any new kind of vehicle design. It's got to be the same as or better than what we have in today's system. Regarding some of the other companies, Comac, for example, I mean, they're beginning their journey. They want to be part of the 99% here, I guess. But, and you know, there's innovation going on there that we're always paying attention to as well. So, anyone else?
Yes, I think you're right. In terms of disruption, I think that all companies are watching disruption in terms of technology that can come from also from Asia. But basically, they have their speed of change and innovation in some sectors which are of interest for us. So it's a worldwide, I would say, technology watch. We need also to be careful, as you said, about disruption in the landscape, so in the environment, how the society is accepting something, what is the pattern of the type of travel, what are the people ready to accept. You were talking that there is a paradigm around speed. You mentioned speed already. There is a readiness of the society, I would say, to be ready to be asked some question. And of course, we are building, I would say, our overall strategy in a moving environment with certain level of uncertainty. And it's our duty as technology maker and as product provider to have this constant watch. So of course, I said we have a polar star with the 2050, and we have a route to go. This is requiring usually partnership and investment on the long term, because in aviation, nothing is very short, because of the safety constraint, but also for the investments which are behind. However, we are in a moving environment, so energy provider, society reaction is changing, so we need to be ready for that. And we are watching it.
Maybe to complement what said my colleagues, if this kind of congress would have been 5 years ago, I think we can see that we are today very disruptive in terms of mindset. We need to face it. It's very different in terms of positioning. We are discussing hybrid, we are discussing hydrogen, SAF, and so on. 5 or 10 years ago, I think probably the Congress would have not thought about this kind of things, just saying the improvement of the single aisle from both Airbus and Boeing, the improvement, but we were discussing point of percentage and so on. And in terms of pure designing a new aircraft, be it in Airbus, Boeing, EMBRAER, or ATR, what you are designing, you have a bad day if you do the wrong design point, or you have really a bad day. So we are very disruptive currently, and in all engineering activities, all R&T, and all programmatic of all companies. Today, I can tell you, this is shaking. This is really shaking. Who has the right answer? We will see, but today we are already disruptive. Coming to your question about China, I think we need to be a bit more open, but today it's, if I take the ATR in China, we are not really present. We were present, but not really. So it has also to be an exchange also in terms of, for sure, technologies, but also openness of the aircraft that we have. So that's my point of view.
We are all talking about open innovation and disruption a lot, but something that does not change in aviation is that everybody expects that the next generation of aircraft will be even safer than the previous one. So safety, it's a key driver. As we say, safety first, quality always, and this molds the way we will evolve and will disrupt in aviation. But for sure, we need to cooperate. We need to keep an eye open. We need to see what some startups are doing and learn with them, because they have speed, and maybe other companies have the experience on how to certify safely new technologies. And with respect to China, I think we must pay attention to them. They did very well on the electric cars. They move it very well, and for sure they will speed up in the airspace, and they will have their piece in the pie.
Next question. There is a question down here, please.
Yeah, thank you. Roland Gerhardt from Germany. So having 4 aircraft manufacturers on stage, there's a question concerning all 4 of you. How far or to what extent do you collaborate in working towards these challenges, like getting SAF 100% SAF certified, finding the right environment for implementing hydrogen batteries on board or something? Does everybody does it by himself, or is there some kind of collaboration where you tackle these huge challenges a little bit together? Of course, you're always competing, but there might be some aspects where you have to collaborate to get things done. I don't even want to talk about open water, where then the market drive would be bigger if you would combine forces and say, okay, this is the direction to go to really have a step change in aviation, and to really say, okay, if we want to have the ATAC chart really there by 2050 net zero, we have to join forces to a certain extent to get things going here.
Yeah, I will start. I have the microphone, but just don't consider it for my colleagues. I will let them discussing, of course. I think it's right, and at I think R&T level, if I look at the US roadmap, if I look at the European roadmap and probably others, I think there could be a way to more collaborative aspects between companies which are competing every day. We need to be clear, but I think it's correct. When I look just on the SAF, I think on the SAF, this is a common view that SAF is unavoidable for the midterm. And here I think just for the to put more pressure on the SAF manufacturers and again additive manufacturers, I see today it's very slow, very slow. There is technical challenges, but it's very slow. And I think all aircraft manufacturers are motivated to modify their aircraft to use it. So just for that, and I think you mentioned the production certification of the new SAF drop-in or non-drop-in. There is a boulevard to more collaborative aspects. Second, I see hydrogen. I think it's very different. So depending on the companies, it will be very different. So I don't want to enter into that. But for example, the batteries, I see a lot of standardization which could be done in a non-competitive way, because at the end we all will buy the same cells on probably the same manufacturers. So that's I see on these two topics. But it shall start, for example, at a very big governmental level to force a little bit collaboration.
Yes, I think it's a very fair questions. And just to bounce on what you're saying, we are already collaborating through some of the framework. The regulatory body is one of the way we are collaborating. If you look at a specification for SAF, of course, this cannot be made alone. So we need to have the energy provider so that we are understanding the production constraints. And we need to have us around the table also to understand what it means in terms of product. So there is a strong collaboration in there. Other example like César 3, so for air traffic management is the full ecosystem which is working on that. And if we want to have trajectory which is really bringing something in terms of carbon or non-CO2 effect, this cannot be done alone. It cannot be just a competitive advantage. It's something that we are doing all together. And the last point, I think you mentioned it, we are starving for weight. So in our industry, there is kind of a common, I would say, question that we are asking specifically to the supply chains. So to the supply chain, like operating conditions and weight, which only aviation is asking, but which is common to all of us. So, and in here, I think we can get out of this competitive question and really being focused on what is enablers more than product positioning.
Yeah, clearly there's good collaboration in the industry in many areas. Well, we're all competitors, and being, competition is great. It makes each one of us better. But there are areas that require collaboration and harmonization. And I think, things around safety, that's an area that collaboration, I think, is I could see more. Where we're headed around sustainability, there's some huge ecosystem decisions that have to be made. That can't be made by one party. That has to be a collaboration. And I think, venues like this, conferences like this, where we can have these debates and really try to get at the essence of what are the things that need to be solved. I mean, that's going to be good for the industry.
So, any other?
Axel, just to
please go ahead.
One comment. Sorry. I think there will always subjects or topics that we will collaborate and others not. When we talk about infrastructure operations and safety and regulations, we will need to collaborate because every one of us will use the same infrastructure and operational rules. Maybe for other subject or topics, we may need to create some competitive advantage, and then the discussions will be more difficult. But we even collaborated on demonstrators with Boeing, and I think this is something that we can all investigate how to do, because everything in aviation takes long and is very expensive. So we need to find out ways to do things and to evolve.
Do I see other questions? Anyone else? There is a question here.
Thank you so much for the presentation. I'm Eduardo from Chile. And I would like to know how well prepared we are speaking about the batteries, because there is a bridge to cross, and this is the battery technology. You have shown a lot of design that relies on batteries. So the question is, do we have that technology available in order that it's commercial, feasible, because you can put tons of batteries in the aircraft and will not you put any passenger in it. So how we are, that's the question. Thank you.
I will start to answer because I'm quite concerned on that, as you can imagine. So yes, with our trade-offs that we made, sometimes some airlines, and I discussed a lot with airlines some years ago, I had some airlines who were just telling me, you have a very good aircraft, which is the current ATR, you just put batteries, and it will do the job. And I had to explain that just putting batteries like this small world, it's simply not working. So that means you can maybe put batteries just to do a flight, but you will have no passengers. And the CEO of airlines that I was discussing with were saying, I don't understand, in my car, in my iPhone and so on. And I said, yeah, but the level of energy that you need is completely different. At an ATR, it's a small aircraft. On a single aisle, it's even 10 times bigger, not discussing about wide body. So yes, the challenge of batteries is quite clear. And by the way, this is why on this kind of, let me say, regional small aircraft, the limit is, do we use a hybrid solution? Because the batteries for maybe, I see a lot of 19-seaters working on batteries only. I see it very, very difficult in terms of density energy. This is quite a challenge. We have big discussions, and I'm sure in our colleagues of EMBRAER it's the same, on batteries and cells manufacturers. But today they need to do steps. As it was done, it was explained on the engines, and Frank yesterday was explaining also that. It's really impressive, the batteries improvement, but still today it's a very low, very, very low density energy. I would dream of something which is at least 2 times higher than today. Not discussing sales management, but also the pack and so on, all the safety that we were mentioning. Hydrogen is a challenge. Batteries are, as you know, the thermal runaway is also a challenge. So,
we need to come to an end. I would like to ask you one final question, maybe for each of the 4 of you, to the audience, because the main part of the audience consists of universities, research organizations, and maybe asking you what your expectations are related to the contribution of those institutions in the coming, and I say, 5, 6, 7, 8 years, because you have been all speaking about products you want to enter into the market around 2035, a little bit earlier, a bit later. But what do you expect those institutions to contribute to that? Is it too late? Should they rather focus on the next products after that? Or do you think those institutions can still support you in the development of technologies for the next product you have been speaking about? Cleiton, if you would like to start.
I think it's never too late. We just need to speed up. And I think the one thing that I see that is evolving is that we are dealing with concepts and having more partners working together on a single concept, because it's very easy to develop technology without thinking about the integration. But what really matters is to see how all the technologies integrated at the aircraft level brings value to the product. We always need to look at the technologies at the aircraft level and all the technologies, let me say, competing to arrive at a balanced product. And in the case we are facing here as sustainability is not only at the product level, but also on the infrastructure and operational level. We need to balance everything, and that's why I think it's not too late. We just need to have more focus, define some concepts. We are trying to figure out the right product positioning. We need to talk also with the operators. They are the ones that will buy the aircraft and will operate, and we need to understand their needs to come up with the right balanced solution for the future.
Cannot agree more. One topic, I think, to focus the energy of R&T universities and researchers on something which is very clear, to do flight demonstrations at the end. This is focusing the effort, putting a time frame to something which is in-flight demonstrated. You can do a lot of research, you can do a lot of things. This is mandatory, but at the end you need to fly. This is our job to make it flying, and after these demonstrations. So that's cannot agree more of what you said, but the flight demonstrator is always mandatory.
Yes, to add on this, we are expecting from your community, of course, to better understand what we don't understand yet. So there is things about the interaction between the product and the climate, for instance, which is still under investigation. CO2 is really the obvious one, which we know since years, but overall, because it will indicate also a route for propulsion system. And there is still, I would say, key elements on which we are talking about core technology. For instance, core technology for propulsions is raising some key R&D question. But beyond that, I agree with my colleagues, we need to talk and we need to understand each other's because a picky and very optimized technology is not the robustness which is bringing, I would say, the level of safety that we are asking in aviation. So we need to bridge our worlds so that we are understanding each other and we understand what are the key parameters that needs to be worked out. And that's also a good thing in the demonstrator. So continue to be deep in the R&D for the things which is your area of expertise, but bridging with us for the key integration question, as you said.
Yeah, collaborations with universities, always an important part of our work. Within Boeing, we've been trying to be very clear on what are the key technologies and needs that we must explore together. And as I said before, and I think we all agree, you must demonstrate those things at scale. Doing them in a laboratory or doing them on paper or by analysis is not enough. You have to demonstrate at scale. Our eco-demonstrator program is a key vehicle for us, where we've got a pipeline of hundreds of technologies that we want to demonstrate, learn from. Not all of them will pan out, but some of them will. Using that kind of platform or some of our other prototype demonstrators, that's where you get the learning, and that is a collaboration with universities and other companies all the way.
Yeah, thank you. And before closing, I would like to advertise the next and the last session in the Global Sustainable Aviation track. I mentioned that at the beginning. It's going to be about air traffic management and the operations around and the benefits coming from that. It's going to be about contrails and the trade-offs between avoiding contrails. And last but not least, and maybe the highlight of that GSA, the airline, Lufthansa, speaking about all of that and trying to make sense about all those technology bricks and operating the product for the best of its meaning. But now please join me in applauding the four people here on stage in participating and in sharing all those information with you. Thank you very much.